Alright, in this problem we're going to look at the work energy theorem and kinetic energy. This is a problem about a spacecraft with an ion engine. Okay, it doesn't say that in the problem, but this is an ion engine. The cool thing about ion engines are that they let out a very small force. You'll notice it's 56 millinewtons. That's the same thing as 0.056 newtons. So that's the force that's being let out. So a very, very small force, but it's able to do it for a long time period, over long, long distances. You'll see the distance here the spacecraft travels is 2.42 times 10 to the 9th meters. That's over 1,000,000 kilometers. So that's pretty dang far that it's able to keep exerting this same force. Okay, and so you can see that we do have a force, there is displacement, and the question is asking about some velocity that's changing. And so the way that we relate force and displacement and velocity is through the work energy theorem. And so we'll go ahead and write that over here, that work is equal to the kinetic energy final minus the kinetic energy initial. You can use an I there or a not, either way is fine. We know that the work is found by taking the force and multiplying it by the displacement, and then the kinetic energy is 1/2 mv squared. And so, of course, this is the final velocity and this is the initial velocity. So from there we should be able to solve the problem by using the information that's given to us. Okay, we know the force. Make sure that your force is in newtons, so 0.056 newtons, times the displacement, which was that really big number, 2.42 times 10 to the 9th. 2.42 times 10 to the 9th, which is in meters, so that's SI, equals 1/2 the mass. The mass was 474 kilograms, so 474, times the final velocity, which is what we're looking for. Okay, minus 1/2 times the mass times the velocity squared, and the initial velocity, it tells us, is 275. So that's probably the launch velocity from the space shuttle, right? Because the space shuttle will take it up in space and then throw it out. Or it could just be the launch velocity from Earth, that when it leaves the gravity well of the Earth, it's traveling that fast. And don't forget the squared here, right? Because it's velocity squared. So from this point, we should be able to go through and get some of these numbers, right? 0.056 times 2.42. Now if you do second and then this little EE here, that'll give you the E, or times 10 to the 9th. Okay, so that'll give us our first number, 13552 with 4 zeros. Okay, so that's quite a bit. I put my comma in the wrong place. Is equal to, and then 1/2 of 474 is 237. Final velocity squared, minus 1/2 times 474 times 275 squared, which is then 17923,125. Okay, also a very large number. And so now I'll be able to move these things around. So I'm going to add those two together. So 135521234. Alright. And we get that number, which will then divide by the 237. And so we got 647,439. And that's probably enough digits that I'm not going to worry about that too much. Final velocity squared. So we'll take the square root. And we get 804.6 is equal to the final velocity. Okay, so at this point, that's where we took the square root of both sides to get rid of that squared. Okay, and so we end up with our final velocity, which is about 804.6 or 805 meters per second, and that's our answer. Ta-da!